this is Koiro with another video for you, and this is part 2 in the Lars Berg Coin game series. And actually this will be my final episode, and you will see why when we go on. And it will be a lot of theory this time. I need to go in more depth of how the circuit works. I also will explain some more about the 4000 series of logic. I will tell you something about fault finding, how to use logic probes, how to read some data sheets, and combining logic and so on. I think this will be quite the useful episode to watch. And it might be some boring parts. I will skip most of the actually measurement and fault findings that I have done. I will only make summaries, because this was a really hard one. And I did find some faults, I did make some new, and I will tell you this when I'm filming from the bench. But first, I will try to teach you some about using the logic probe to find faults on a board. And I will give you some theory in between. So let's first start with a walkthrough on the project, and I will give some more in-depth about the situation and stuff, and then we move to the bench. Yes, as you can see, I've called this part 2, the saga continues, and we are going just to do some repetitions and also take some new findings since last time. This game is actually now standing on all zeros here, and that is the fault that the game had when I got it. Not the game, but the board actually. And I've discovered that these two and these two should be one part of the counter and count up, and these three numbers in the middle is part of one count sequence. And as we might remember from last time, this is showing the last winnings you had. So by the way the board was explained to me when I got it, all these was on zero, so there was no counting going on. And that's about the same that we discovered last time. There was no counting, but now I have gone into a really deep dive into how this works, and I'm only going to give you a bit of overview, because it will really be too much. I could make this video a whole day long and explain some details about this circuit, and they might not even be right, because when you don't have the schematics, there might be some connections and some strains of logic that I have not uncovered yet, and that probably is the case. But this is the board, and we are having some switches here that we are going to check out later. And we also have some other peculiarities with this board. But first, this was not something I showed you in my last episode, and that is actually this sheet here that is contained within the box. And there also are copies of this on the internet, and I do think they are the same. I made some English translation of the important parts as we go along. But I didn't read through this in detail before I started last episode, and there are some interesting information here that actually can tell us something about our fault situation. And you actually have one line here that says, if all numbers on the front are zeros, check LD1, LD2 and the tilt. And the tilt is this strange contraption here that is, if you are bunching the case, this will actually bounce down and make contact here, and you will get an alarm and the counting will stop. This is something that we will see when we go more in depth in the circuits. It's also stated that the LD1 and LD2 should be lightning. And it's not very apparent to me how this actually is connected together, but they say here that the LD1 is lightning when there is a throughput through some signals up here, and the same with the LD2. But this is connecting to part of the circuit that I don't have on me, so I was measuring out and I made some connections here to fix this up. But is this right? I'm now getting the right logical levels, and I'm able to get these ones to light up. So I'm probably in the ballpark. And the tilt switch is working as it should. That's already confirmed. But there is a lot of other things that also can go wrong. And it also tells us about adjustments and stuff. We will get further into that. But all in all, this is meant to be operated by the one that is owning this, or the one that is maintaining this box, to change some parameters and also do fault finding. And what do we have inside here? And there are some user serviceable parts here. The first is that you can actually control how the counting should go. And here you can see that I have divided between the middle three numbers and the two numbers on each side of that. And that is useful information for us. And they also have put on this chart here that tells us how these switches should go. And the switch 4 is always off on our settings here. I don't know, I have not checked if it's connected to anything. And here you can see what display, and these switches here is the maximum value, and these are the start value. So you can start on 0 or you can start on 1 and so on. But this is only 2 switches, so you only have 4 positions, so you can start them all on the value 3 when they both are on. Or they can start at 0 if they are put on off, both of them. And this is for the middle numbers, and these are for the numbers that are on the side. And that means that both the numbers on side of the tree in the middle, these ones here and these ones here, are controlled together. If they count together, I'm not really bothered to check. And these are adjusted together. And you can also adjust the speed of the changing on the numbers, and that is also telling us something. So this is adjusted by the R3, that is this potentiometer here. So this is controlling one oscillator for changing the numbers. So this is telling us something. And this is the counting speed for the counters that's actually showing the values on the screen. And this is all the adjustment that actually are described here, and there is no more user serviceable parts here. There is no more potentiometers and no more switches in this box. And before we continue with measuring out and using our logic probe and doing some other measurements, I didn't really go into depth on this last time, and that is the difference between TTL logic and C-Mos logic when it comes to logical levels. This is something from my last year's Christmas calendar, when I walked you through a lot of TTL logic and explained quite a bit how this was working. And these are actually turned the opposite way, because it's showing the input voltage here and the output voltage on this side, while this is showing it the other way around. The input voltage on a TTL circuit is high from about 2 volt to 5 volt. And low from 0.8 to 0 volts. And the output voltage is defined narrower to have some security margins, and it's 0.5 volt and 2.7 volt should be output voltage as a high. So that leaves us with this gap here, and this gap here as noise immunity and load immunity, and some difference between different series and so on. But on the C-Mos logic on the input is defined as being high on this side and low on this side. And it's 30% and 70% about of the drive voltage. And what about the output? The output on a C-Mos circuit is almost always the same as VDD, or almost 0 volt. So it's not illegal or undefined, all this on the output, because the output and the input is almost the same when it comes to measuring the threshold. But if there is no load from the outside, then this is almost always true, that it's almost the same as the drive voltage and same as the ground voltage, that's 0 volt in our case, when you are measuring outputs. So that means that you have a symmetrical situation when you are measuring on stuff. So it's very easy to see if something is broken or not. And there is one more thing, and that is on a TTL, an open input is always defined as high, and that is not as clear on the 4000 series of logic. So this was just meant to give you some variation that the logic probe you are using can't, even if you are measuring on 5 volt, if you are using this in C-Mos modus, it will actually detect something like 1.8 volt as a low. So that's useful to know when you are dealing with interfacing this, and also when you are doing fault finding. So there is a big difference between these, but you can of course integrate them together anyway if you take this into consideration. And now we are going to start measuring out on the board, and I will show you some things. But first, I have done some measurements on these already, and Tommy was peeking around and was not sure what was making the oscillation and what was driving the different clock signals on this board. And that was my first goal, to find out what actually is the oscillators on this board. And we do have a 40-106, so we actually have 3 of them, but one of them is acting as an oscillator, and it's connected between these gates, like you see in the schematics down here. And this is the circuit that is doing the counting on the digits on the front. Because here you can see that this is actually connected to the R3, that is the adjustment part, and it's a 1 mega ohm potentiometer, and it's in a series with a 56k resistor. The capacitor is connected to the input via a 1k resistor. And this is a bit different from the one that is our reference circuit here, and that is actually this 1k input here. And I do think that this is to suppress noise, and also to decouple some static electricity and other stuff that can come if you adjust this potentiometer when the power is on. So it's basically the same circuit, and this is oscillating with about 113 Hz. I did get measurements from 110 to 113, so it's in that ballpark somewhere. And this is, as I said, one oscillator. The other gates on this is used for other stuff, as a normal inverter. You can also do some measurements here, some calculations to see how this actually goes, and it's based on this curve here that is being made by this capacitor charging, and then this is switching and the capacitor is discharging through here. So I won't go into detail how this works. I can do that in a later video if you want. And the other oscillator that we have on this side, you can actually see here the signal that is coming out is a very nice square wave. It's about symmetrical. It's a very nice fine square signal. And this one over here is also using a Smith trigger, but this is actually one gate of a 4093B that is a NAND gate. So it's also in an inverter, and you can see here they actually used it as an inverter. This reference circuit up here is just tying this to high, but here they actually have connected both inputs together and made a very simple oscillator that is the same as the reference circuit, with a 56k resistor and a 10 nanofarad capacitor. And this is actually oscillating with 28.3 kilohertz. So this is a frequency that is going, mixing some signals, doing some reset, doing some set counters and other stuff. I really not gone into depth on this because this seems to be working, and the signal is divided by some counters here and there. I can tell you a little bit more about this later. And you can see this signal is not totally symmetrical. You do have some measurements here for making this transaction and making calculations for this. And that the signal is not symmetrical is probably due to some load or voltage or some things, because it's not stated here. It's stated that it should be about symmetrical. But there are a slight difference here that might account for some of this. But all in all, it's a stable oscillator. It has been stable all the time, so it just works and it gives this signal. So these are the two clocks that actually are here. I have been looking for more oscillators in this circuit and have not found anything that leads me to believe that there actually are more than two oscillators. So we are going to show you some measurements on this with the probe later on. And this is another circuit that I will go into more in depth in the circuit. And when I say that this frequency here, the 113 Hertz, is the one that is doing the counting, 113 Hertz, that's quite a fast counting when you are only counting to a number below 9. So, or 9 or below. So it's of course being divided someplace. And this is what these circuits do. This is the CD4024. And the CD4024 is a so-called ripple counter. And it's a lot of flip-flops that is coupled in series. And you can actually see here what it does. This is fed the 100 and from 110 to 113 Hertz signal from this clock, and by here it's divided by 2 I mean, so it's 56 Hertz. On the next output it's divided by 2 again to 28 Hertz, 7, 3.5, 1.7 and 0.8 Hertz. So all of these inputs are giving the half of the one before that in frequency. So this is quite slow. 0.8 Hertz is about once in the second. This is changing a bit lower because 1 Hertz is 1 time in the second. And this we are going to find in the circuit, and we are starting our tour now to the bench to see how things works. Yes, we continue this where we left off last time, and what we did discover was that this IC here, and also kind of this one too, but they might be heated up from this one. But this is a 40106. If you see here, I'm just connecting the power, we can see where it's starting to heat up. So you can see here there is two of those. Is this one here and is this one here, and this is a Smith trigger. There is no reason why this should be hot at all, and as I said, none of these is drawing any power. They should not be hot to the touch. I'm just connected the power again, and we can see here this has a background temperature of 26, and this board has about 26. There's some heat from this overhead light here, and let's see here, this is 30, 27, 41 already, and 29, 26. So I do think that we are just going to take out this and see what's happening. We can of course try to replace it with just another chip, but I don't even know what this chip is doing here in this circuit. And this was one of the chips that actually was changed before Tommy got this board, because you can see here this is one of the white sockets, and the other 106 actually has this socket too, and the 4093 also. But I just connect the 12 volt again and check if these neighboring chips now is keeping within the ambient temperature. It still has it's closing down, it's decreasing, and this too is also decreasing, so then this chip was what kept them warm. But Yeah, I will connect the 24 volt again as well. It's this one. I just took on this one to make sure I got the proper chip and that it was heated. We did have some clock action. Yeah, here I'm just probing around to check if there is any clocks. Last time we did have several clocks that we was able to identify on this. And I'm just probing around to make myself a bit acquainted with what's going on. And remember, we are doing this now without the 106 that we took out. So it's just to see if the board is completely dead without this, or we will get about the same results as last time. Okay, this was giving a clock last time. Well, there you can see this one is still counting. It's a counter. Check the datasheet. This is the 4516. One of the lots and lots of counters that's here, and if we see where it counts, this is actually the carry in. So this is an input signal, Q1 is output, and this is carry out. Okay, that's a bit strange, because this other pulse here is for the up-down counter. That is, as you can see here, the carry-in signal. And the carry-in is, as you can see here, carry-in is pulsing. So it's not, it's being no count and count up. So it's maybe they use this as an inhibit signal and it comes from somewhere. And they have the other line that is counting is the up-down. And up-down is also an input. If it's high, it counts up, and if it's low, it counts down. And this is not edge triggered, and this is pulsing. And the third thing that is pulsing is actually here the carry out. So carry in is an input signal, and carry out is an output signal. The carry out is normally marking when the counter has an overflow, and that means when it counts from 16 or 15 to 0, it will give a carry out. And also it seems like this is giving a pulse out when there is a carry in pulse and the counter is on 0. As all data bits on the counter is 0, then it will get a 0 from one transition on the carry out. So this is pulsing the same as the carry in according to the data sheet. Okay, this was where the fast pulses was, and this is the 4518, and the 4518 is this one. It's also a dual up-down counter, and let's see where this is. Okay, the enable A and Q1A, this is the output, and output, and output, and output. So this is actually counting, but it's not counting via the clock, it's counting via the enable. And that is what we see here. It can use the enable to count if the clock, if this one is 0, low, yes, then it can count on this one. So this is an input for this, and it's increment counter, and here you can see it's counting on all. Oh, this is also counting. This is the reset signal. So this is counting up and it's stopping. Reset B. Yes. So this is also counting via the enable signal, negative flank. But where does this pulse that we see here, that is the enable, and what comes to the reset. Where does these pulses come from? I can of course just turn off the power and try to own this, but I will probe around a bit more to see if I find these pulses. And you have this one, 4093, and this is the same one that is coming in here. And what is the 4093? The 4093 is this gadget here, and this is probably the oscillator thingy, because this is also a Smith trigger. Let's see about that, how this is connected. So pin 3 is an output. Both these are low and this is high, and this is of course the VDD. This has an undefined level. And this is true with both pin 1 and 2. As we can see, they are connected via a capacitor to earth and via 56k resistor to the output. So of course this is an undefined level according to our datasheet that we were saying. So this is ramping up the pulses that the Smith trigger gate is making a perfect square of on the output. Yeah, at this point I'm not really sure what is causing the frequencies to happen, the oscillation and stuff. So I just here unplug the 4093 from the circuit and see if I lose all the counting or wave action on this board. Because as we know, there is more than one oscillator on this board probably. And I'm just checking to see if this one is making all the frequencies. And of course we now know that they are not. And of course what I did here with unplugging a C-Mos device without disconnecting the power, it's not the way to do it. But this time I was lucky. Now this one is clearly the one causing this to actually work. Yeah, and here again just plugging it back in like it was some other TTL device. Sometimes you are both stupid and lucky. So this is the oscillator circuit. And if I turn off the power like so, and then I try to use the ohm meter to see here, yeah, just use the noise, the beeping. What you will see here is the way of fault finding these kinds of things when you don't have a schematic. You take an output and you find out where it's connected, or you take an input and find out where it originates. And this is very time consuming. I'm just checking to see if there is any more connection. So if this is where the clock originates, then the output to all the other clocks must be connected to one of the Q outputs. This is the good thing about the Fluke. It will beep at once if you get a connection here. Okay. 4073. It's these output registers, and it's, what pin was it? It was okay, so it has actually two connections to that one. I will just mark them. So you have... Whoa, and you think things have been boring up to now? If I was going to continue this, you would be bored to death, because this goes on and on and on, and I do follow most of this logic, but it keeps biting itself in the tail, because as you can see, this goes into an AND gate, and clock signals going into an AND gate. That's typically used as a switch or an inhibitor for this signal, and it's a lot of these things going on. So I have just shown you the methods I was using to map out the circuit and check that every trace and signal was going where it should go. But I won't show you any more of this, but I will show you a bit more of how to use the logic logic probe as a means of fault finding on these kind of circuits. But what we did find out was that this counter here is taking its signal from here. And this counter here, this is the 4518. I can turn on again. Sorry. So this one is counting and actually making this counting pattern here, so it's a frequency divider. So this is generating the other clocks. I'm pretty sure of that, to the other chips. I actually lost some footage here, but what I discovered is that this one here, that is Q4 here, the most significant bit, is coupled to the enable pin here. So this is the clock input for this one, increment counter. So now I do know that none of these bits actually matter. It's this most significant one. It's connected to the next counters. They are just cascaded together. And that means that I can continue this with the cues from the other one. Okay, next bit. Okay, so, and this is Q2B. And when we follow the traces, we see that the Q2B is connected to an input on an AND gate on the 4081 on IC14. So this is another example of things biting itself. It's going to an AND gate, and the A gate is probably either functioning as an inhibitor or as a mixer of signals. So this was just to give you an idea how to follow up on all of these clock circuits in this rather complex mix of circuits. So I will now just continue to a general part to show you how to use the logic probe as a fault finding device, and we will also use it to find actually a fault on the board. And you also have IC6 pin 3 and 11, and you have IC15 1 and 26 4, this one. Yeah, so there are some clock action going on. But I will try to turn off the power, and I will try to put in 106 here. I don't have a lot of 4000 series logic, but I do have some, and I do think I have 106 here. This seems like a brand new chip. We can test that. Yeah, but just see what happens. I will turn on and we will check again to see if it's get hot. You can see the ambient temperature risen to 28 because of the overhead lights. But now it's not getting hot. The 106 is a Smith trigger, and we do have a pulse here. And 1 is an input and 2 is an output, and this is oscillating just fine. And here I did loads and loads of measurements, both with the Fluke in the beeping modus and with the logic probe. And this was to trace the signals and the signals path for various stuff. But this is the hard part when you are tracing things that is connected together with resistors and other logical chips. The 106 oscillator is feeding its signal to 2 AND gates, and one of these AND gates is feeding this further to the 4024 chip, that is the one that we was showing in the start of this video, where we showed off how this ripple counter actually is supposed to work and how we have found it working. So we have traced the oscillator signals through AND gate and into the 4024, and this is how far I will go with this. And it was lots and lots of measurements, hundreds and hundreds of measurements to check this one piece of the equation out. But in this case it actually paid out, because as I was checking things, I was noticing that the 4024 was not doing what it was supposed to do. So this here is actually not doing what it should, because in this data sheet we have the input pulses on 1 and we have reset on 2, and if it's low it's not resetting, and 3 should be counting. So 3 should be the most significant pulse, and it should not change so often, but it should be changing. So this is not doing what it should. Yeah, let's try changing it and see what happens. 4024. Do I have a 4024? Yes, I do have. I don't remember if this is some China parts or if this is new old stock. I could also see in Tommy's stack to see what is there. But let's try. 1, 2. Yeah, now it's doing what it should. And does that change anything up here? No, it does not. The 4024, it's only one of these here, but now it's at least doing what it should. So now we got something, but I will just now take and use the ohmmeter again. This is really some tiresome shit, because now I will test this one to see if this actually was used at all. And it was the 4013 on IC04 we had used. And IC04 is flip-flop, the 4013, and it's maybe used as a memory cell, a one cell register of some kind, a frequency divider. I'm not really sure. It can also be used as a debunching device, but probably not here since it's going straight to a clock output. So I'm not sure what this is doing, but it probably is related to the storage situation with this counter for the last winnings, or some other things. I'm not sure. But this is the kind of things we are seeing here. It's well connected logic, but it's very hard to figure out what everything does. When you use the truth table to actually check if something is working, it's very useful to have this in front of you. And what you actually do is to just check what the signals should be. This one here, the 1 and 2 pin on the 4013 should never be the same. So if this is low, yeah, this is now pulsing, and this is pulsing the opposite. And you can have these here that is not pulsing. They will have their outputs like so. And you have the opposite outputs on the top here for the second pack. And the same for these ones. And you have a 4013 over here too. Yeah, this is actually pulsing now, that's good. But you see this one is pulsing on the clock, so that's an input. And it's not pulsing, no, this is the 4013. It's pulsing on the clock but not on the output, and that means that the reset pin has to be stuck at high. Because when the reset is high, they will have their effect and it doesn't matter what the clock is. And the same with the set, that's pin 6. That's a low. And when the set is low, it actually is able to count. So this probably is low on every one of these. And that means that the reset is used to keep them from counting. And the clocks on these is pin 3. And on this one it's pin 3, and on this one is pin 3, and you have, yeah, that's the 4 of these we have here. So the 4013s, it seems like they are working as they should. The problem here is that nothing is triggering the reset to be able to do their job. If you try some of the switches here, can we see if that changes? It's still high. And if we take a simpler circuit, like the 4071. The 4071 is an OR gate with a quad 2 input OR gate, and if we check what's going on around here, the A and B should make a high, and it's the other way around here, so this is a low, that means both this should be low, and the same on this side, low, low means a low, and here you have a high, that means that at least one of these has to be high. And we can also check the others while we're at it. All these are low, this one is pulsing, and this one is pulsing, and that means that this one also is pulsing. So this is combining two pulses. They are different frequency, so this is probably included in the randomness as I described earlier. Yeah, and here are everyone is low. And the last one of these is this one. Low, low, that means that should be low. This is low, that means that these two should be low. And that's low, and that means this should be low. This high, this low, that means this should be high. So the 4071s, they are probably working. And we can have the larger gates, and this is an AND gate. The AND gate, it is that all the inputs should be high to get a high. And we do have a couple of these, and we have the 3 input and the 2 input version. The 4081s is the 3 input version, 2 input version, sorry. So we check that first. The pinout is described here. So this is low, and this is pulsing. That means that this should be low. So this is an inhibitor. If you put this high, then the pulse will be getting through. So this is used as a lock, a logical gate that is locking the signal. If you put this one high, then this signal here will be fed through to this output. And let's see the next gate. Low and high. This is also a pulse. So, but this inhibitor was low. That means that this is also low. And on this side, low, high, that means low. And here we take it backwards, high, that means that both these should be high. And the 4073s, we have one more, 4081, it's this one. This is pulsing. That means that this is pulsing and this has to be high. And it is. And on this one, this is low, and that means this is low. And this is pulsing, and that means this has to pulse and this has to be high. So this one is doing its job nicely. And we have the 4073s, and they have a 3 input, and they are actually a bit strange in their in how they actually are working, because you have the inputs down here and you have the output of that up here. So input pulsing, input low, and input low. That means that this one up here, it's actually this one. No, and it's not even that. It's A, B, and C. So it's A, low, and C, and low, of course. And then you have the D, E, and F. They are actually close together. D, E, and F. And they also have an inhibitor here on the D pin, so it's not getting through. So that is correct. This is the output. And for the next gate, you can see is the G, H, I, and they are all combined up here. Pulsing, it's low, and pulsing. So that means that this should combine these two pulses, but it's not doing that because this is low, and that means that this output that you have here is low. So this 4073 is working, and then it was this strange. They have the same pulses. and this has the same pulses. So this should give some kind of pulses on the outside. And you can hear here they have combined all the pulses, so that works. And the next was the D, A, and F. And this is low, so this should be kept low. Okay. And the next was this, low, low, and 1 pulse, and that will be 1 low. So the 4073s and the 4081s appears to do their job just nicely. So we can also check, we checked this last, but the 106, and I actually missed one of them because this is also 106. So we have two 106s here, so there is a bit wrong in my previous video, and you have the 106 here. And these are quite easy because they have an input-output like so, input. And pin 1 here appears to be floating, but of course it's the input pin or the sawtooth pin of the Smith trigger oscillator. And this is input. And this should inverse that. And input high, output low. And on the other side, and input, output, and input, a slow oscillating signal, and you should find that here also just inverted. So that means this 106 is good. And what about this one? Yeah, just take my word for it, all the other 106s are okay and working as they should. And I have gone through all the logical circuits here and confirmed them in the same way. So this is how you use the truth table to determine if a chip is good and bad, and that is the best use case for a logic probe actually. Yeah, but now we have changed our 4024. We have actually done some more fault finding. We have jumped some wires, but why don't it count anything? And there is one important aspect of this. And the 4516 binary counter do have a reset signal. These counters can be cleared by a high level on the reset line. And as you can see here, if the reset is set high, then it doesn't matter what all the other signals are. It will be reset and it will be showing all zeros on the output. And also if the set or PE, that is the preset, then you will see it also doesn't matter what the others are. It will be the preset value that is loaded into these P's. And you can see these P's down here is the one that is taking the input from the switches that we described earlier. So if you set this to count from 3, then these will be a 4-digit, or not 4 binary digits value that is loaded into this. And of course, in our case, it will be 1, 1, 0, 0, or the other way around. And the case that we do have here is this reset pin on these ones. It actually, or reset, this one, the reset, the 9. It's actually kept high on all the 4516, so none of them are actually doing any counting. And as we saw when we measured around here, the clock signals or the preset enable or carry in on some of them is actually receiving some pulses. And we do have some other counters in the circuit, most noticeably these 4013 flip-flop gates. That is also a lot of on the board. And these are also kept reset by doing a low and a high on the set. Then you will have these values. If you change these the other way around, you will have these values, regardless of what the data or clock will have. And this is also a situation we see, and I've tried to describe this in the circuit down here, where I've just described one of the reset lines for these two circuits here, IC8 and IC9, that is counters. And they actually is connected, among other things, to the tilt, as we saw earlier. and they are also connected to the monostable flip-flop, the 4538, that is being used to set a fixed pulse length on something. And it's also connected to some other circuits around here. And it's totally impossible to go all the way back and check all this, because it's lots and lots of circuits that's biting into the neck of the one before that. But it's good to know, and it's easy to use the truth tables of these circuits to check if anything is right. And as I showed you in the sequence earlier, is that if you have your truth table for how this is going to work, I'm only showing 2 inputs here, even though we have some gates with more inputs. If you check an inverter and have a 1 in, it should be a 0 out. And if you have a 0 on the output, it should be a 1 on the input. It's quite easy. But on an OR gate, either one of the inputs will drive a 1. On a NOR gate, both has to be 0 to get a 1. All the others will drive a 0. On an AND gate, you have to have both as 1s, otherwise it will be 0s. On an AND gate, it's the opposite. You have to have both as 1s to get the 0. All other conditions will give a 1. And that is the key to do fault finding and actually mixing back together here. But what I find on this circuit is there is a lot of these resistors and diodes that is also doing combining of inputs, and also to set biases on inputs. Like you see here on these circuits here, this VDD is connected to this inverter here when this switch is not pushed, and this is the tilt switch. So if you give this a tilt, it will actually bounce to a 0, and this 0 here will give a 1 here, and it will drive the reset. So if the tilt is high, then this will reset. This circuit up here is, as it is now, driving a 0. That means that you have one of the situations here. So either both of these are 0, one of them are 0, and in this case this is a 0 and this is a 1. And these are also driving the resets on these 4013 flip-flops here. And there are lots of these counters, and some of them have connected resets, some of them have not. These two have resets coupled together, and a couple of the others also have resets coupled together. That means that they are kept in a 0 state together. So this is not a very easy thing to be able to fault find, but at least we now have a much better understanding of why it doesn't count. It's basically because all of these are kept reset all the time. So that is something that have to be remedied. And why are these zeros? We did get a clue earlier when we saw this fault finding guide, where you did have the LD1, LD2 could tell us something, and you also have to check the tilt. But there also are other inputs that is driving this, and that's why I can't finish this repair. All the yellow marks here are the different reset signals, and I measured all of these reset signals is kept in a state that inhibits counting. And some have common dominions that will switch them, like the ones on these counters here and these here. They are connected to this tilt and some other logic circuits. Among other, they are connected to this connector down here. So is there something that should be connected here that will drive this reset? Probably. And you also have this pin here, the second pin on the power supply. That is also a feedback signal that should be kept high for something here to work. It will give some of the signals here if you give this in high. And this is coming from the power supply. So this is kind of a power good thingy. I have simulated that to see how things work. You do have also these two down here that I have looped on this connector up here. You can see the two arrows here, they are pointing to two signals, and this is actually the LD1 and LD2 control signals that we talked about, and these are meant to be fed back from a board here that is doing the sensing of the coin operation. So these are Are they part of the circuit? I'm not sure, but if there are zeros, we should check these two. And I've both tried with one light, with two lights, or I say lights, but it's really the control signals here that is feeding into the logic. These LEDs are only part of the diagnostics. So I don't know how much of the reset actually needs to be put low before anything starts working. I have forced some of these low and I can get some feedback. And you have the truth tables here for the 4013s and the 4516s. And they will tell you that there are other situations also that can inhabit counting. But as of now, all of them are reset. But some of these set signals here on these counters, they are not just tied permanently to a level that they should have, the low level. But some of them are tied to other logic, and that is probably also tied somewhere to these switches here. Do they read this in every time? Probably. So each time this should start counting on 3, for instance, they have to put this set signal high to make this start counting here. So there are some feedback into these set signals too, and I have not looked into that in detail. I do think that this is these counters here that actually are affecting this, but I'm not sure. I have not bothered to look into it either because there are too many uncertainties on this board. And we fixed the 4024 chip that actually was missing the significant digit. So is this all that is wrong? It could be. And there also are some other things on this board. This is a lot of bad soldering and other stuff. But mostly, I don't really know if this is broken anymore, because it can be bad connections. The fault can be on the other boards that should connect into this. And we also got an explanation why there is so few signals up here, because we now know that of the digits that you have that is counting, it's, as it is now, it's 7 zeros that is showing up here. But we do know that it's only 2 different feedings on this. So these probably are the same, and these 3 here probably are counting the same. And even if they are not, I do think that we have chosen to use so few signals here tells us that they actually do count the same. And all the other counters is resetting, they are dividing the frequency, they are keeping track of your score, and so on. And you can do this a lot of ways. And you do have the last winnings digit here that actually needs a 4-digit feed value to have been put into this to show the last winnings. This actually can be used both a counter with the set, and you can also use the flip-flops that is in the 4013 counters. So there are a lot of options here. There is a lot of unknowns. We don't have the schematics. So I can only do this 2 ways. Either I send this back to Tommy and he can try the card as it is to see if it actually starts working. He can start with some of the fault finding that we actually have now uncovered to see if that works out. And we can also check on some of the other signals when he actually have connected this to the board. But at least I will be able to help him a bit more just by the work I have done so far. But a schematic to this, it would have been gold. A schematic for this, and this will have been a really fun process, and I could have mimicked all the control signals without doing. I wouldn't need any of the other boards at all, because the schematics will tell me what I need to interface into these other plugs here to make this work as it should. So I could have mimicked every signal if I just had the schematics for this. So I will send this back to Tommy, and I'm not giving up on this board, but it was either sending him the board or he had to send me the rest of the whole cabinet and chassis with other stuff. And it's not something you just put on a cargo. This is quite valuable stuff, and we must make sure that it's not in a worse state than it was when we got it. So that's about how far we got with this, and the story is continuing, but it's continue with Tommy in Arctic Retro. So that's it for this video. If I have shown you all the footage that I've done with fault finding and making myself really good acquainted with this board, it's about 5-6 hours of footage. Something of this would have been really boring. I'm not saying that this movie is not boring, but I have tried to put in the interesting parts, and what you will learn from this video is fault finding with the logic probe, and also a bit about TTL versus C-Mos logic, and some practical issues with logic, of course. So that's it, and hope you enjoyed the content. The board is now going back to Toby, and we will maybe follow up on this on his channel, Arctic Retro, and we might see a happy ending on this if he connects the board and it actually works. Who knows? So that's it for this episode. Please like and subscribe, and I really need you to go and look at some of my older videos. I do need the view time to go on a good foot with YouTube's algorithm. But see you in the next time, and thank you for watching.